shift.
Thank you, Lil. You can all hear me, yeah?
Yes.
Good. So, hello everyone. It's great to see all the participants that actually join us for the user meeting. Some of you have attended many user meetings, and you know that we used to organize them in Norway. We used to meet face to face and discuss and create a network. Now we are online, and there are some advantages of being online. It's the large group that actually could join. Today we have people in India, Chan in China, and I've even seen one participant in New Zealand. That's probably rather late for those over there. And on the other side, there are some that have been up very early to attend this meeting, and probably a lot that have registered that doesn't join because they will look at the recordings afterwards. So obviously there are some benefits of an online meeting as well. So I have two small technical presentations. The first one has the title Rotor Equivalent Wind Speed. So let's have a look at that. Next, Lil. I actually meet with WindSim user and potential users almost every day. I ask them, why do you do CFD? When I discuss this, I often get the feeling that in some cases it's because, well, our client asked for it, or maybe the bank asked for it. Maybe you feel experienced, you have been in this field for many years, and it's the natural next step to go to CFD because it's supposed to give you more accurate wind modeling. So in a way, I feel that some people just would like to have a green check. We do CFD. But next, Lil, what we would like to do and what we would like to see is, of course, by delivering this, you actually increase the profitability of your wind projects. So that's the purpose of this small talk, to see how you really can do a more proper post-processing to actually create this increased accuracy, not only stopping at the CFD flow simulation itself. One more. So in this presentation, we look at how to increase the accuracy of the AP through using rotor equivalent wind speeds. Next one. So what is a rotor equivalent wind speed? Well, it's maybe you can take the next one as well. It's much easier to explain when we have an illustration. So you know that when we calculate the annual energy production, it's based on the mean wind speed at hub height. But then some years ago, back in 2017, it was introduced in the standard a procedure where you could divide the rotor in slots, and you can calculate an average wind speed in each of these slots and combine it due to the area of that slot. So here is kind of the definition. And by doing this, we would take into account the effect of complex terrain, or maybe a terrain where you have a forest, where you have high stability, basically areas where the profile doesn't really match what you see on the test site where the power curve was established, a flat area. So this is a potential improvement on our annual energy estimates. How did it start? If you go to the next slide, Lil. Well, I attended tech workshop in the US many years ago, and at that time DNV published a white paper on what is the status today, how good are we in establishing the annual energy production, the pre-construction estimates. So they compared many sites with actual production data, and the outcome was not that good. We actually saw that it was an overestimation of the estimated production by almost 10%. Okay, this was a great dilemma for the industry. So of course, if you take it, yeah, you can take it one step further, and even one more. That's good. So of course, the whole industry looked at their procedures, and we were aware that there were many areas where maybe we made too optimistic estimates. The measurement campaign, the long-term correlation, the flow modeling, the wake modeling, maybe we were a bit too optimistic. So DNV, they made maybe better models, maybe more conservative estimates. At least they have an updated version of this white paper. And today they claim that they have very little errors. It's only a few percent. But if you look at this also updated presentation, you would see that the spread, the times you actually do an underestimation and overestimation, is still there, which to me is an indication that, okay, maybe we only do more conservative estimates, but we haven't really improved too much on our modeling. One more, Lil. So one of the main reasons at the time, people thought that one of the main reasons for this too optimistic estimates was due to what they called site-specific power curve. We needed site-specific power curves, because if the site have a lot of turbulence, well, you cannot expect to have the same production, even though the profile is the same, to a site where there is lower level of turbulence. Some turbine manufacturers started to give out power curves for different turbulence levels. We will not look at that, but we will look at the sites where we have different shear. So this is how we kind of, this is many years ago, remember, and then years later, then it ended into the standard to allow you to do this so-called rotor equivalent wind speed. One further. Yeah, we learned about this from a contributor, Francesco Castellani, a professor in Italy. He have attended many user meetings. Unfortunately, he's not joining us today, but he showcased this many years ago. He had sites nearby where he is located at complex sites, and he of course observed that there is no log profiles. There are other profiles. There are negative shear profiles. So how does it come that they will produce the same? So he created an article back in 2005 and showcased that this is actually a big problem. Next one. So to illustrate, you have a power curve that is obtained at the test site, flat area in Denmark, Germany, but then you are on another site where there is not a log profile, and what the turbine actually experiences is that it doesn't follow this power curve that was established at the test site. So we will try to deal with that. Next one. So when I deal with a problem like this, I like to make a simple model to just highlight what is happening. So of course, I make a cosine hill. So here is just the dimensions of the model, and also showing the inclination. It's a rather steep hill, so there will be a recirculation even here in this hill. Next one. And this is then the numerical model, 1 million cells towards a 10-meter resolution in the refinement area. Next one. And I don't bother to do all wind direction. This is a symmetric case. So I run one wind direction, and that's the wind from 180 degrees. So I run that until it's converging. It doesn't take long. It takes 15 minutes. And all the other directions, I don't care about. I just run them so that I can actually create a report with energy estimates at the end of the WindSim procedure. So if you go to the next one. Yeah, here I've actually rotated a bit the model, but what I showcase here is that I'm only looking at the climatology where I have wind from south, 180 degrees. I've positioned my measurement mast towards the border, towards the inlet, and then I've placed a number of turbines going over the cosine hill. On the upstream side, I will have realistic profiles, which many turbines will experience. Of course, on the lee side, if there is a recirculation, it's a bit extreme, So some of these turbines are located in the recirculation zone, and I just skip those as part of the AEP estimates, although the speed will be that low, so it would be zero velocity in any case, but it's not realistic, of course, to look at the production in a recirculation zone. So go to the next. Yeah, here is an illustration of my single case, wind from south. Here you can see, actually, yes, there is a recirculation, and I also display the wind resource map. And you can see, of course, there is large variability in a case like this. So let's look at how the production will be. Go to the next. Sorry, not the production yet. I've just also showcased and highlighted the profiles for some of the turbines. Turbine will show a log-like profile. One more back. The first turbine number 1, it's in the upper left corner. It shows a log profile. Then I just take turbine number 4. The shear changes. The shear changes all the way towards the top. And then I have turbine number 9, which is on the hilltop. Then I have a negative shear. And then I go towards turbine number 13, which is just before the recirculation. It has an, well, it's slightly inside the recirculation, it looks like. It has an extreme shear. Yeah. And in the next slide, Lil, then we will see all the profiles for the turbine number 1 is at the upstream, and then it's 100 meters in between each of those. And you see how the profile changes until on the lead side it recirculates. Remark that here we look at the 2D speed, so it will always give a positive value. So you have a kind of an inflection point here towards the last number of turbines. It should have been negative values, but since we look at 2D speed and see the absolute value, it doesn't show the recirculation, but you can see when the you see this inflection point there, the recirculation happens. So it is turbine 16, 15, 14, and slightly 13, which is within the recirculation zone. Okay, then we will look at the annual energy production. So we go to the next slide. So in the first, I simply create 2 layouts. So I have one layout, and then I specify that I would like to run normally with energy estimated by the speed at hub height. And then I create another layout, and I turn on the rotor equivalent wind speed calculation. And then in WindSim, you have to choose certain number of slabs that you divide the rotor into. It could be 3, 5, 7, or 9. I've picked 9, and then I've recalculated, and I get a somewhat different energy estimate. It's a bit hard to read this table, so I've made it in a plot. So if we go to the next. So these are the orange line here is the energy estimate turbine by turbine when you use the hub height. The blue one is the annual energy estimate when you use the rotor equivalent wind speed. And what we can observe is that they are quite similar. Actually, it's a difference of minus 2%. You will get a lower estimate if you use the rotor equivalent wind speed. Also remark the large variability. I mean, the lowest production is at the turbine that is upstream when the wind slows down before it kind of accelerates over the Kåsan Hill. And it's a variation of nearly 7, a factor of 7, 6.8 is the difference between the lowest and highest production. Now I disregard the turbines in the recirculation, so they will not be producing in a situation like this. And you can see, as I said, turbine 14, 15, and 16 doesn't produce at all because it's too low wind speed at that location. So this is the kind of big picture. But if we look at it also turbine by turbine, then you will see that there is a variation for the upstream turbines as the shear gets first higher and higher, and then it turns into the negative shear. So with the highest shears, then you have a discrepancy of -2 to 4.5% for the turbines upstream. The turbines at the hilltop will actually have a positive contribution. I mean, it will have a higher AEP when you use the rotor equivalent wind speed. They are the one with the negative shear. And then it gets, of course, quite extreme towards the lee side with a very, very high shears there before it separates and you see it recirculation. Then you have a -9.8% difference and even almost 30% difference whether you run it with hub height or rotor equivalent wind speed. Okay, I think there is maybe one or two more. Here is the summary. So we have showed that we will hopefully increase the accuracy by using this rotor equivalent wind speed. For my artificial wind farm over the Kåsan Hill, I had a change in production by 2%, a bit more. And the turbines that are the most extreme one with high shear, then you will see even higher discrepancies between hub height wind speed or rotor equivalent wind speed. Yeah, I think that's what I have on that topic. I guess that we'll take some questions afterwards. The next one is even shorter. It's on time series versus frequency distributions. This is a topic that we have showcased in our training sessions for many years. But every now and then, when as I said, I discuss with people almost every day, and I'm in some cases a bit surprised that there are even really experienced wind analysts that are not fully aware about this dilemma that we should use time series when we do our post-processing and not frequency distribution. So I've just brought up some of the slides, renewed it a bit from the training session, and I will just like to highlight this fact here. So if you take me to the next slide, Lill. Yeah, it's the same question. It's all about accuracy and doing a proper post-processing. So we skip this. This is the same introduction as I had for the previous. And as I said, in this presentation, we will look at how we can increase the accuracy of the AEP estimate by using time series instead of frequency distributions. That's the purpose. Next one. Yeah, if we have a frequency distribution, we have a discrete representation of our measurement campaign. So we have taken our time series of measurements, and whenever we find measurements within a certain interval when it comes to the wind direction, a certain interval when it comes to wind speed, we lump it into a single point, which is the points of the frequency distribution. So we could think of the orange area here. Here we have taken all the measurements from within the orange area and put in the center. And then if we should manipulate that, and we always manipulate the measurements in any kind of simulations. I mean, we take information from the measurement location and we move it to turbine locations by using what we have in the CFD simulation: shift in direction, shift in speed, shift in turbulence. So this manipulation we do all the time. So let's say that in a case I have a speed up, I will move something upwards. I have a change in direction to a positive directional shift. I could move this into, say, the blue area and the cross here in the blue area. But that's not allowed. I cannot be there because it's not one of the points of my discrete representation. So I have to move it to the existing points in my discrete representation. And this is the problem we have, because then we kind of smooth. Well, we have called it a redistribution error. But we have to do some kind of redistribution. That's our problem. If this was a time series, then we could have stayed there at the cross, because then you can be everywhere in this space. So with time series, you don't see this. Let's look at an example, the next one. Just to highlight, very, very simple case again, only one wind speed from one direction. But here you will see the problem. If I have a speed up when I go from position 1 to 2, in this case, it's a reduction in speed. It's a speed up of 0.9, and I have a negative shift in direction of -10 degrees. So I end up with the wind climatology, as you can see under point 2. It's a bit reduced and it's a bit shift towards left. And here, remember, there is nothing wrong with my model. If I go in the opposite direction, it's just the opposite speed up and directional shift. But then I end up with something which is not my original. It's smoothed. It's due to this redistribution error. So here it's highlighted how this could be. Then the question is, how large are these errors in a normal case? So then I bring up our demo case. Next slide, Lil. This is the Hunhammer case. I've put up all the turbines as well, because again, I would like to measure the consequences on the annual energy production. How large do it actually varies, whether I do a transfer of the measurement through a frequency distribution or through a time series. Of course, I do this all the time. As I said, whenever I move it to another turbine position, I will apply this. But now I do an artificial exercise. I just move the climate data to another arbitrary location, and then I move it back again. And I would like to see that it should remain the same. In order to do this, I of course need a measurement which is recorded as a time series, and I have one, a 2-year-long time series at this location that you can see here. And then arbitrary, I just moved it 1 kilometer towards the north, and then I moved it back again. And I've done this using the technique of moving around a time series, but also the technique I've just explained to move it as a frequency distribution. Of course, I've then created a frequency distribution version of this time series to do the manipulation as a frequency distribution. Okay, so let's look on how this will look. Next slide. One more. So this is the original climatology. It has a wind speed of something, and now I will move it to the northern position. One more Lil. And then it changes. Of course, I'm in another area with other wind conditions. So yeah, it changes quite a lot. And then I move it back. One more Lil. And here's the problem. I should have had exactly the same. I don't get exactly the same. And if we look at the numbers, I've created a small table there as well, so we can take one more Lil. The original wind speed was 7.89, up there north, 4.4. Okay, that's probably the conditions up there. But when I move it back, I would like to have 7.89, but I have 7.54. And you see then the difference in annual energy production. One more Lil, there were many small steps here. The difference is 4.5% in the annual energy production, whether I use the original or one that I have moved around and degenerated in a way by using a frequency distribution. Okay, what's happening if I do the same exercise as time series? The next one. Okay, one more. Again, the original. One more, we move it to the north. It's another climate up there. And then we move it back. One more. And it looks more similar. Let's look at the table. One more. Here we get almost the same wind speed and almost the same annual energy production. There are only small differences here. One more. So here the difference is 0.1%. There are still some differences. So if we look at the next slide, I've just looked at the time series I took the kind of first numbers in the time series. So I have the original, and the first 5 records showed me this directional and this speed. And then I move it north. Okay, it's another climate up there, and I move it back. And I see, of course, there are some abbreviation errors because we use, in this case, only 2 digits. Maybe we have to improve on this as well, but maybe we are quite satisfied with the accuracy we already have. But there will be, of course, some abbreviation errors in this manipulation as well. If not, I would think we should have exactly the same results. Okay, one more. Yeah, so this is the summary. So we have showed that transferring climatology as a time series doesn't introduce any redistribution errors. So you should always avoid to work with frequency distributions. It's a bit strange, isn't it? Because during all these years, the most used output from WinSim is the frequency distributions or the wind resource maps of WASP, where we even have done a Weibull fitting. So I would claim that we have degenerated much of the information we have established in the CFD model by going through that path. Much better if you would like to take WinSim results, move to other tools, use the raw CFD results, as you can do with FlowRes. And you have heard that we have this cooperation with WinPro to do this even smoother, or also to OpenWin. That's a much better approach. But you can, of course, stay in WinSim as well and do this the way we would prefer, and you will have time series with energy production at the end of the road. Okay, thank you.
Thank you very much, Arne. Very interesting. Vincent, do we have any specific questions, comments that we want to pick up from the chat?
There is some comments, no questions. So but it seems it was a very interesting and good presentation. And thank you, Arne. This is awesome. Great explanation. So that's the comments. So okay. That's good. Thanks a lot. And no questions as per now.
Thank you. Okay.
Well, great. Thank you, Arne. We are then on a break. We were a little bit late, 10 minutes or so. So we will start 10 to 1 in 10 minutes from now. We will start with user presentations, and I'm going to